Hey guys, this week should be a little bit shorter of a week. We're not going to do too much. I want to start off with the top here. I have all of our exponent rules that we learned last week. This first bit's just kind of a review. All right, so I'm going to do a couple of these and we'll move on. All right, but with this first one, we have the natural log of 4 plus the natural log of 6. All right, because we have the same base, right? They're both base e. We can combine this into the natural log. Sorry, I told you I would do a better job of that. The natural log of 4 times 6, which is the natural log of 24. All right, which we could then plug into our calculator and get an answer of about 3.178. All right, and the rest of these are pretty similar. This next one you're going to divide, so you actually get the natural log of the log base 9 of 9. All these kind of work out the same way. All right, so go ahead and try those on your own and then check your answer on the answer key. All right, down below, another quick review is just converting between forms. All right, so the first one is if we are in exponential form, we have e to the 12th equals x. My base is going to stay the same, so if I want to go to logarithmic form, it's going to be log base e. All right, but what changes is my input of 12 becomes my output of x becomes my input. All right, so I have the log base e of x, which is the natural log of x, equals 12, and that's how I would convert it. Okay, you can do the same thing over on this one. All right, and then I want to try this last one, or this last type, just to show you, so we can move on. All right, when I convert back, right, we use that swirl method. All right, so I get 6 to the second equals x minus 4. All right, which actually is 36 equals x minus 4, and we could continue to solve this if we wanted to. I'm going to go ahead and do it because it's not that much. And get x is equal to 40. All right, and that's what we're going to end up doing today. Towards the end of this is solving these logarithmic and exponential functions. And one method is going to include just switching the form and see if you know anything different. So let's go ahead and solve some exponential equations. All right, so this is the first thing we're going to do. Sorry. All right, so we're going to solve exponential equations. And the first method is pretty straightforward. It's when you have the same base, or you can write them as the same base. Right? So I have 125 to the x equals 25 to the x plus 1. Now, obviously, these are not the same base. All right, but what I do know, some information that I have just because I've done this a few times, and you guys probably know, is 125 is actually 5 to the third power, and 25 is 5 to the second power. So what I can do with these is I can switch this, and I can write, instead of 125 to the x, I can write 5 to the third to the x. Instead of 25 to the x plus 1, I can write that as 5 squared to the x plus 1. All right, and then using my exponent rules, when I take a power to a power, I can just multiply those exponents together. So what I really get is something along the lines of 5 to the 3x is equal to 5 to the 2 times x plus 1. And what we hopefully should notice is that our bases, 5 to some power equals 5 to some power, are the same. That means these exponents also has to be equal, right? So I can continue this up and finish this up by saying, well, 3x has to equal 2 times x plus 1. All right, and then solving this is just solving a linear equation. Finish this up, I get x equals 2. Sorry about the noise in the background, that is my daughter. But go ahead, try these next three. All right, check your answers on line or on the answer key, and then move on. All right, the next thing that's not quite as easy is when we don't have a common base. Okay, so well, as we can see here, you can try if you want to, but there's no way you're going to be able to write 8 as a base 23 or 23 as a base 8. We're kind of stuck with what we got here. All right, so this is where we're going to use the inverse property of logarithms. All right, and actually we're going to rely on is that third log rule from before. All right, that third log rule lets me take the exponent out. All right, so what I can do is I can pick any base I want. Some people like to pick the base 8 because it gets rid of this here. I tend to either use the natural log or stick with natural log of x, or the common log base 10 of x. And I like both of these because I have these on my calculator. My calculator does this for me. All right, so it's something that's really nice. And what I'm going to do is I'm going to take the logarithm of both sides. All right, what that means is when I look at a to the x equals 23, I can take the natural log of both sides. Natural log is a function. It's just like I can square both sides or add 2 to both sides like we did before. I can take the natural log of both sides. So what I get is the natural log of a to the x is equal to the natural log of 23. All right, which is nice because, like I said before, that third log rule lets me take this x and bring it out in front. So what this becomes, let me get back to my pen here, is x times the natural log of 8 equals the natural log of 23. Well, it doesn't look like it's that simple, but natural log of 8 here is a number, right? It's about 2 point something. Actually, it's probably a little bit less than 2, 1 point something. But I can divide by it. It's just a number. Right, I can end up with an equation of x is equal to the natural log of 8 divided by, oops, sorry, not natural log of 8. Let's reset there. X is equal to the natural log of 23 divided by the natural log of 8, which is approximately 1.508. Okay, so what I want you to do is, again, try these other ones. All right, one thing to kind of hint or to get you on the right track is in this next one and the last one, take your exponential and isolate it first, right? So you're going to, this second one, I guess, you're going to subtract 6 and divide by 3 before you do anything. And the last one, you're going to add 2 before you do anything. Okay, so try those out. Exponentials, not logarithms. All right, the last bit is going to be solving logarithmic equations. All right, and there's a bunch of different ways. There's not really a clear-cut way to do these. We'll do a couple examples. But most of the time it's going to be, if it's not in the form that you can use, switch it to another form. This first one here is actually, our calculators can actually do this. We can switch it to a different form, but it's actually in a form that we can use because the log base 30 of 4, that's a number, right? There's not much to it. It's a number. It's saying, what power do I take 32 to get 4? Right? It's not a great number, but it's a number. And we can actually evaluate this using that change of base formula. Right, if you guys remember that change of base formula. If you don't, go back to the last week and look at the change of base. It'll explain it for you. All right, but what the change of base formula lets me do is when I'm evaluating log base 30 of 4, I can evaluate that with any base I want. Right, so I'm going to switch to the natural log because my calculator can do the natural log. I'm going to take the natural log of 4 instead of the log base 30, but then I'm going to divide by the natural log of 30 to make sure I have everything I need. All right, and this is approximately 0.408. Right, so we can actually just solve that one as is. All right, the next one, similar to what we did earlier this section, right, just a couple minutes ago. We can't do anything with this because the x, or the unknown, is within the logarithm. But what we can do is swirl, switch it to a better form. Right, I get x to the third power equals 6. Well, I don't know what that is, but our calculators can take a third root. We take the third root, and we get that x is equal to about, I'm going to put my squiggly lines, 1.817. All right, so we can do these. So far, we haven't used any logarithms or exponentials other than what they are. We haven't used any of the solving techniques. This last one on the top row, sorry, is almost identical to that one in the first page. I think it may actually be the second one from that first page, that I left for you guys. All right, but when we swirl this, all right, swirling it is a little bit trickier because we don't actually see the base in this natural log, but the base is e. So the swirl tells me e to the 12th power is equal to 6x. I can solve this by dividing by 6. Get x is equal to e to the 12th divided by 6, which is approximately 27.125. Oh, never mind, not 27.125. I can't read my writing. It's approximately 27,125.794. Much larger. Okay. These last two are going to be very similar to the ones we did before, the ones we just did here. Swirl, switch to exponential form, and you should be able to solve from there. All right, these other ones are very similar to the exponentials with the same base. All right, because if we notice here, these are logarithms. They're both base 8. And because they're base 8, it doesn't really matter about anything else. We can't really swirl them. But if I know that the log base 8 of something equals log base 8 of something, those somethings, so those inside pieces, have to be equal. So once you have the same base in a logarithm, we can just go straight to, well, x plus 6 has to equal 4 minus x. All right, which is convenient because this is just a nice linear function to solve, right? So I can add x to both sides, subtract 6, and then I get 2x is equal to -2, or x equals -1, right? The not crazy thing, but the thing we should do is check our answer. It doesn't show up too often, but once you're dealing with a logarithm, you do have the possibility of an extraneous solution because you're dealing with a restricted domain. All right, so just go ahead to check your answer, take the log base 8 of x plus 6 and plug in -1, and it equals the log base 8 of 4 minus -1. Right, and most of the time, because we're not doing much else besides just solving these, it's going to work out fine, but you should get in the habit of checking. So you get log base 8 of 5 equals log base 8 of 5. You can plug that in your calculator if you want, but I will tell you that those are exactly the same thing. They're going to be equal. These last two, or this last one, is almost identical. I'm not going to do the whole thing, but there is a one little startup or one little setup to it. First thing we should do is notice we don't have a single logarithm over here. These are both log base 10. Well, actually, all three of these are. But what I want to do first on this left side of the equation is write this as log of x over 4 using that second logarithm rule. That equals log of x plus 7. All right, and what we can do now is the exact same thing as above. All right, we have a log base 10 equals log base 10. So x divided by 4 is equal to x plus 7, and you can solve. All right, not much to it. This last one is identical to the ones that we've been doing above, right? All these up here, right? Except for now we're going to reduce this left side like we did on this problem here. All right, the first thing I want to do is write this as log of x divided by x plus 3 equals 1. Once I have that written, I'm just going to swirl. All right, I'm going to take base 10 to the first equals x over x plus 3. So 10 to the first equals x over x plus 3. And then I would solve this one exactly the same way as that I've been doing. Right, I'd multiply by x plus 3, x plus 3. I would get 10x plus 30 equals x. 9x equals -30. X is equal to -27, or 3, sorry, -3.3 repeating. All right, 27 would have given me exactly 3. All right, and that is how we would solve exponential log. That should be about every type of example. Again, this week's a little bit shorter, a little bit of a review, but go ahead and look at these notes and see if you have any questions. I would check the answer keys as well, and make sure you're trying all the problems that I give you.